mi Canva. We go to our physics 312. I have put at the end on lessons, right? So in lessons, you have everything. You go to lessons, you have Prof. Moi's thing, and then here comes my thing with the different chapters, the different, here you have the lecture notes, you have the video, you have the Nielsen model, just the chapter. You just have to read the first pages, as I say. You have the Nielsen diagrams that you can always go through. Rotating nucleus, the deformed shell model video. This is very interesting. And then you have the PowerPoint sent by Ray Carsten from Yale. And he asked me to tell you that that this, whatever he write down at the beginning, is there is no such thing as a stupid question, right? Leon, come here. Leon? Toma. But you need to practice the ball.
I did.
Okay, then play. So then rotational linear parallels. Okay, and we go back here. And then at the end, you have I'm going to make a few more appendices. You have here all the tests with the solutions, test, solutions, test, solutions, and short explanatory videos here, which I'm going to, instead of having these long videos, I'm going to shorten some of the concepts, so you can just go to the appendix and see clear what concept you have to do. I'm going to give some bonus points to those who send me real pics of work being done, of your being. I know some of you guys don't have everything, all the calculations in your notebook. This is not the way to have it. You can have it, but this is I always like to have the good calculation, the final calculation on paper. The rest go here into the bin. So it's a way to test that we are actually working every day, as Einstein used to say. I'm not calling it myself. And then I wanted to show you one thing. Here there will be tests and quizzes. There will be a test and quiz given for Thursday. And there will be a bunch of questions, question pools. I have lots of question pools with lots of questions here that I've been working out. But the good thing is that what we are going to do with these quizzes is that I'm going to leave it open for you to go anytime you want and make a quiz. It will give you, I will assign the quizzes in a way that you get immediate feedback, right? So basically you will get the solution, or you will get the mark. And you will see which questions you did wrong, right? So in such a way, you can practice as many times as you want. I encourage this to happen. Maybe not of this question, none of these questions will be in the final exam, but it will be very helpful. They will be very helpful for you to understand the concepts. And once you understand the concepts, the final exam will be much easier, right? This is all about learning the concepts, and maybe some of the questions will be in the final exam also, right? That will be the possibility. Obviously, you're not going to make all those questions in the final exam, otherwise it's very easy. But I want, after the test on Thursday, I'm going to leave it open, and every time you go, you can make your own quiz. Every time you will get different questions, different quizzes. I encourage you to do it as many times as possible. All right. That's everything I have to say. And unless you have anything to ask, this is your opportunity. So you always ask a question. Who's that?
I just wanted to ask regarding Thursday. So you're saying that there's obviously, every time we take the quiz, there's going to be different questions, right?
Thursday there will be a test. So there will be one set of questions for everyone. So there will be different questions to everyone. You may have 2 questions which will be the same, but for the test, all the questions are randomized. After that, after the test, I'm going to leave it open, Salman, for you to go there and run the quizzes as many times as possible, because every time you go there, you may have a repeated question or 2 repeated questions, but the question, you have different questions all the time, right?
Oh, okay, I see, Prof. Thank you.
But the test will be on multiple choice, just to practice this conceptual physics. But remember that the final exam will be bucket, will be bing, 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 calculations, calculations, calculations. So don't think it's going to be just to click here, to click there, A, B, C, D. Multiple choice are good for conceptual physics and to understand the concepts is okay. But in physics, I want you to see I want you to give me the calculations that you have done. As I say, there may be one question or 2 questions which come from the multiple choice, maybe 1, no more than 1 per final exam. Something similar to those questions. Never the same. So don't think that I'm going to ask you the same question I asked before. So there will be something always different. I spend many hours trying to invent my own questions so that you can actually learn from that without looking at Google. Google is not our friend here. Google is only our reference. Our reference to get this equation L equal I omega. For that, we can use Google and check hyperphysics or whatever. But in terms of the questions, don't go to Google, because these questions are invented, all of them. So there won't be, maybe there's some guy out there who invented the same questions, but it's difficult. Salman, very well done with test 3. You did a great job. And Craig Smith also, and Shoki as well. Songeso, you are always improving, and you're always asking a question. What is your question today?
I have no questions unless I have a problem solving that equation for E is equals to the one for that one as 3/2. I only get 1/2. I don't know how you add.
Okay, the one over that's yes, for the harmonic oscillator.
Yes.
So the 3/2 is just a conversion from. I just multiply by 3 to make it 3 dimensions, right? That's it. So the 1/2, you get 1/2 with what you are doing is 1/2.
Yes.
So at the end, that's right. So you just multiply by 3 to make it 3D. Okay. It's as simple as that.
Because I use the what you call it, the annihilation and the creation operators to find the equation, but I couldn't get the 3/2 at the end. Only find half. So you multiply by 3.
That's a very good question, Songeso, because that's not explained there. But the three, not the half, but the 3 is just a matter of making the system a 3D system. Every real system is a 3D system, right?
Okay.
So there's not much of anything there. There's no calculations. What I want to remind you. I was talking to my postgrad students right now. I want to remind you one thing. So in quantum mechanics, when you have operators, let's say, I always tell you that xp obviously is different to px, right? That's why when we have xp, and this one is xp minus px, right? Which is equal to minus x I respect to the x I h bar here, minus I h bar x. So the order, this is 1. but there is nothing here, so this is 0. So this is equal to minus minus plus IH. So, and this is the uncertainty principle. But, and this is actually what you need to prove that A dagger equal to 1, right? But then I want you to remind that A plus A dagger, anything to the square, is not going to be as we always see, equal A square plus A dagger square plus 2A dagger, right? This is not going to be the case with operators. Don't make that mistake, because A plus A dagger square will be A square plus A dagger square plus AA plus A dagger A. This is the correct version of running this. Is that clear? Guys, this only applies when you have, variables, x plus y square. When you have operators, with operators that doesn't apply. As I say, I always explain this. If you have, you can take your, it will be in the class, I will take the eraser, and at the eraser, I will rotate it 90 degrees. So the eraser will be there, and another 90 degrees up there, and the eraser will end up on a vertical position, right? If I do the process, the other process around, if I move this guy first, so let's see whether we can draw this. So let's say I move this 90 degrees up there. So this will be like this, and then rotate it 90 degrees around this axis. So the end of the whiteboard will look like that. But if I do the opposite, the end point won't be this one, right? So you can take something like a eraser or your calculator. Let's take the calculator. Easy. So you take the calculator, and let's say, okay, we have my calculators here. Let me just see. Here we go. And I'm going to rotate it 90 degrees this way, and then 90 degrees up there, right? So we go back to the original place. If I do the same thing, 90 degrees up there and rotate like this, you see the final point is different, right? So this is the same situation that happens with the operators. That's why XP is different to PX, right? As I just showed you, the same orientation with the calculator, you will end up in a different place, right? In a different orientation of the calculator. If you do the step, the first step second and the second step first, right? Is that clear, guys? This is just basic quantum mechanics. Clear to the 1, clear to the 2, clear. So, anything else? Shoki, anything else from your side? Chad, anything else?
No, sir, nothing from my side.
Ansel, do you want anything?
No, sir, nothing on my side, sir.
So then, one last thing, actually, let me share the screen one more time. I want everyone to go through the course evaluation. So we have a lot of discrepancy here. The module was well organized. Remember, this is term 2. Okay, the course evaluation, there are only 6 responses. I want everyone to respond. I want everyone to respond So we have a clear understanding of the situation. I know there were some students who complained, but I want to see what the overall picture is, right? I want to see what the whole class is thinking about the lectures and what we did within the circumstances, but we don't blame any circumstances. I mean, I think it was a beautiful course for all of you guys, but you can see this is what we are having here. Work hard to make the subject interesting. Someone 50% strongly agree, but there's a lot of discrepancy. So basically, I want the full class to come to this course evaluation and tell me, it takes 5 minutes to do it, and tell us what is the situation, so we can go to the HOD and to the D and say, look, this was a successful course, or it wasn't a successful course, so we have to improve this and that, So, but it's important that we have not only 6, but the whole class. We have at least 30 submissions, or the 39 will be ideal. So we know what you all think. So
Prof,
tell me.
From lecture 2, there was a question where you asked the radius of silver.
Right.
Then there was this part where you said the kinetic energy in the center of mass is equal to 1/2 of mu, u1 squared.
Right.
Then you said mu is the reduced mass.
Right.
Is mu a constant, or we also have to calculate mu?
Mu is a constant, is the mass. Let me check quickly. So this is a question which no. So so let's see here. So we have that always we are considering when this guy actually move so we assume that this was delta x. Actually, very important, guys. We assume that this delta x is equal to 1.5 Fermi. But we can go back to the plot and not assume that, this is what I want you to investigate. We have the whatever the sigma, the omega, and we have the energy of the alpha, and we have these data points, right? These data points, which suddenly we can explain with the classical electromagnetism, but then suddenly there's a deviation at some point, right? At this particular energy. And this is where our Rutherford theory fails, because Rutherford is classical, right? And now suddenly the data points come down here, and this is an indication that we are waking up the nuclear force, right? So to do this problem, I assume, or you assume, that the radius of the alpha particle was given by 1.2 a to the 1/3 Fermi, right? But then also I can ask you the following question. I can assume that also the radius of the tantalum is such, whatever, given by 1.2 a to the 1/3 fermion, right? Fermi. So then I can tell you, I can ask, what is actually delta x? So you can actually deduce the range of the nuclear force, which was a given before, if you know the radius, if these are the given, right? So the question here will be, what is the range of the nuclear force? What is the range of the nuclear force? That's a question which is the same, but without delta X as a given, right? Basically, you can deduce the range of the nuclear force by using these kind of plots, right? And knowing where they start touching, because you increase the kinetic energy. This is the kinetic energy, T. When they start touching, at this range where they start touching, this delta X is when you have this deviation, right? Then you can apply, again, the V center of mass equal T center of mass. So now let's answer that question in particular. This was a situation where I just changed the problem, deduce the range of the nuclear force instead of deduce the radius of the tantalum of the silver. But in that particular situation where these guys get together, this guy is coming there and this guy is there, whatever is, this is the radius of that particle, this is the radius of the other particle, and this is the range of the nuclear force. So basically, T center of mass in this particular case equal V center of mass, and this is equal a mu U initial square, as you just mentioned. And then here we have set 1, set 2, E square, with in our system is 1.44 MeV Fermi, right? Divided by actually the whole thing, 4 pi epsilon naught, this whole thing, and divided by R, which is, or by B, let's call it B, which is this whole distance here, right? From the central points, that's B. So now what we are done with the reduced mass, this is called the reduced mass, and is given by M1, M2, M1 plus M2, right? So then here, what you do is, obviously, this is going to be given, you have M1, MEV. So you can take this one in AMU, in atomic mass units. Basically, you take from the tables of whatever nuclei you have. We can go here and you can open, actually, you can open the, I think it was in the lessons, in one of the first chapters in the nuclear properties, you have all the masses here, right? Here. So in here, you can calculate, you can control S and say, okay, I want the 12 carbon. So this 12 carbon is 0 because it's the reference, but let's choose another one. Let's say 178 hafnium, that one, okay. And this is the reduced mass. You convert the reduced masses to atomic mass units, and basically you have that easily calculated. The idea of the reduced mass is that we are simplifying a two-body problem into one, which simplifies tremendously. So you're going to have basically, this is going to be MeV per C square, MeV per C square, and this is going to be MeV plus 1 MeV per C square. So you're going to adjust 1 MeV per C square here, because they have 2 of these and 1 here, right? So then the initial velocity, which you are going to determine by 1/2 of mu1 squared, because this is the kinetic energy in the lab, and u1 is the initial velocity of the alpha in this particular case, or the alpha. And these plots, this is very important, these plots always give you T-lab, right? Is what we measure in the lab frame, the different kinetic energies in the laboratory frame. But for this to be equal, you need to use this you need to use the center of mass frame. Center of mass frame, you get the reduced mass from the tables of masses, get them always in MeV, Fermi, all these H bar C is a very, very useful MeV, Fermi. Then you have the 931.494, right? MeV per C square, which has an atomic mass unit. So, and then you have E square over 4 pi epsilon naught in the Gauss system, which is 1.44 MeV Fermi, right? So these are very important units which simplifies the problem dramatically, and the fact that you may make some mistakes is reduced by that, right? So so did I answer your question? Is it clear now?
No.
No, not yet. So tell me, Petile, what is unclear here?
Rob, when now calculating for mu, do we substitute the value that it's constant, which is 469.14 MeV per c squared?
Sorry, say that again. I didn't understand what you were saying. Say that again.
Okay, now when substituting the reduced mass, do we use this formula M1 M2 over M1 plus M2
Right.
of helium and a silver or something else?
Right.
The value which is constant.
Right. It's constant. Of course, it's constant because the masses are all the same, right? So that's right. So okay, let's go to that point in particular. So basically, you have the reduced mass, which is equal M1, M2, M1 plus M2. Right. So we take the mass, the M1 for the helium. M1 from helium is going to be 1, and the M2 will be the one for tantalum or silver, right? So now, important to remember, here is where's my PDF? Here. So important to remember is that, let me see, I could read, not this one. I could read chart of nuclides. No. So if we go to the silver or to the tantalum, I just want to say, oh, this was too far. I just want to know which silver. Let me see. 2, 3, 4. Here we go. Silver. Here. Here, silver. So here we have Ag is silver. So so which one? Both of them are quite relatively abundant. So you can choose any of them. Let's say the mass of 109 or 107. So basically, I want to go to the 107 mass here. You can choose any of those and say, okay, 107 silver. So from here, you are going to determine the reduced mass. I have a little spreadsheet, so I'm going to just copy this one. I'm going to make everything for you. So this was yesterday, the moment of inertia, but we can do the same thing. We can call it this something else. Reduce mass. Okay, so I'm going to do the following. I'm going to put the excess mass here of the silver. So this is 107. Oh, let me go back. So 107 silver. Right. Here we're going to put 107. And this is the reduced mass. We'll make it bigger. This one here, 14. I'm going to change this and multiply by 1,000. So I'm going to reduce this this guy here to make it in MeV. So this is the mass in atomic mass units, and this is the mass in MeV. So then we're going to have the one for the alpha particle. Let me copy this one here. Yes, I want to put here a 4. And here I'm going to put the helium. And this is basically you get the mass excess from the tables, and then you convert it by multiplying that mass excess, dividing by that mass excess by 931,494 MeV per C square, which has an atomic mass unit, and then plus the mass of the of interest, 107, right? I'm showing it here, so I can put this video later on, but this is, write it down how you get for the mass excess from the tables, you get the atomic mass units here, and basically you just multiply that by 931,494, and you get the mass in MeV per C square. And here we have for the alpha particle, we can go also to our table and say 4 space helium, and this is our excess mass right here. We can put it right there and say okay, and then we're going to multiply by 1,000, so I'm going to put the 0 here. I'm going to make it the same thing, 14. All right. So then here we have the atomic mass for the helium-4. So if we want to calculate the reduced mass, let's put it here, reduced mass. So we will be equal. So open brackets, mass 1. We can put mass 1, the mass of the silver, plus the mass of the helium, divided by the mass times mass, right? And actually all this has to be multiplied by, because now it's in atomic mass units, but we want to convert them to MeV per C square. It has to be multiplied by 931.494, right? And that's it. And this should be the reduced mass of the system. Is that bigger? Actually, remember the units are very important in these units, because at the end we have multiplied by MeV C square, right? So reduced mass in these units. Makes sense because the reduced mass is M1, M2, so M1, M2, we did it right there. M1 plus M2 divided by M1 times M2, right? As I say, always memory is a bad or a girlfriend or a bad boyfriend. Will always betray us. So we always check and see. That's why Google is important, but although Google sometimes is confused. Remember not to believe anything, but just here we go. M1, M2 times M1 plus M2. Let's see if I did it right. What happened here now? What was that? M1. See, I did it wrong. So it's M1, M2. So M1 times M2. That's why I multiply by 931 actually. M1 plus M2. Right? So M1, M2 in the numerator. M1 plus M2 in the denominator. Memory is always a bad boyfriend. All right, guys, or a bad girlfriend. Let's not be gender based here. Remember, this is actually the reduced mass for the system of silver and alpha particle. Is that clear now? Petile?
Yes, Prof, it's clear.
Okay, good. So I think I see Craig is getting there, is getting ready with the whiteboard. That's very good to know. So I'll show you this video. I post this video, but it's very so basically you get the mass excess is M1, M2 divided by M1 plus M2. And you can use any units, but at the end, you know that it's going to be MEV C square. And also, just for us to double check things, we just one last point, always we double check. Oops. I want you guys to go here and select. So what is, so we have 1/2 of mu U1 square equal, as we say, Z1, Z2, let's call it E square, which is 1.44 MeV Fermi, E square by 4 pi epsilon naught divided by B. So B has to be given in Fermi. Let's see whether it's true or not. So mu is going to be MeV. I just using the units now. MeV per C square. U1 square, if you get from the kinetic energy, the lab energy, will be M1 U1 square. So the lab energy is the energy that you have in the graph where the situation deviates right here, which was whatever. Let's call it 20 MeV. Let's call it MeV also. So basically, U1 square is going to be MeV divided by MeV C square, right? So basically, MeV cancel. So it will be just C square. So we go here, and again, B is gone there. So B, actually, let's start from the beginning. So B will be, so MeV Fermi, because this one remains there, right? These are the proton or the charges of, this has no units. The charge of the alpha is 2, and the one of the other one, I don't know what this is right now, for the silver. So B goes there, MeV Fermi stay there. Then we have down here MeV per C square from the mu, and the U1 square is C square, right? U1 square in C square. So these guys, units, they go away, these guys go away, and only we have the Fermi. So we always do a check of the units to make sure that everything is okay, right? To make sure that there's no MeV here, an atomic mass unit there, which remains, obviously the calculation is wrong. So we always play with the units in whatever we have. Here, I just put B here, and then this goes into denominator, and that's what I'm using the different units, right? So I'm not even calculating U1. I just need U1 square, actually. I don't need to know what is U1 because C square goes with the C square, right? So simplicity is very important. So that's why we are using these units in particular of MeV, or Fermi, and all those constants that you know so well. We make things simpler, we make less mistakes. Also, important, memory, not to trust memory ever. No, one day you remember, next day you don't.
Prof,
Yes, okay.
I just want to ask for the beta minus decay and the beta plus decay, as well as the electron capture. Is the Q value always negative, meaning it's always exothermic?
So what is the difference between a Q value negative and positive? So it's not always negative or positive. Negative Q value means that you need to add energy, means that you have in chemistry, it's called an endothermic reaction. You need to provide energy for the reaction to happen. If you have a positive Q value, the reaction is exothermic, which means that the reaction will happen spontaneously. You don't need to provide any more energy. So for these particular cases, we can actually have a look. And I'm going to share now again. I'm going to here to this guy. I'm going to open another Acrorit toy PDF where I have all the case here. So I'm going to check right now. We're going to have all the case. Actually, everything here. Okay. Let's go to something heavier. Okay, the Q value here is positive, you see, from fluorine 15 to oxygen 14. But this is an unstable transition. So from fluorine 15, we go to the chart of the charts of nuclei. So we go to the first one, 61, 161, I11. If we go to 1, we go to 15. This is an example we just shows 15, which is quite 15 fluorine, it was, to oxygen. This now. No, this is a proton. You see, this is a proton. It was a surprise that you don't have the same number, 15 and 14. So that's not a beta decay. Here we have. It's a beta decay, but let's see. I want a proper. Here we go. So you see a positive Q value here, oxygen 18 to fluorine 18. So if we go here, this is oxygen neon 18, which is here, to fluorine 18. So this is by electron conversion, and the value is positive. So it's not always negative. It's shocking. I mean, that's not only will be negative when you need to provide energy, and the situation doesn't happen spontaneously. So we can check more. Actually, I don't know if I send you this this toy file, because it's very interesting to look at the different beta decays. Here we go. See, beta minus is also positive. So it basically means that it's an exothermic reaction, and it will happen spontaneously, right? So I don't understand now, Shogi, where did you find a negative Q value? Negative Q value will imply
I
that
was asking Prof, because in the assignment when we had to do it, we weren't given a specific element. We just had to like say whether Q value for beta minus is positive or negative, and we haven't gotten feedback on that assignment. So that's why I was asking. Yeah.
All right. That's very important. So so that assignment, let me look at the assignment first so you can remember. So here it is. So let's look at the Canva. So that was one of the first assignments, right? Lessons in beta decay. Here we go. So there was a video, which was the lecture 1 or 2? Shoki?
I'm not quite sure, but there was one you did where it was beta minus decay.
Right. So here probably this. So let me see. This is the one I did, right?
Yes, Prof.
Okay. So basically, we are applying Einstein formula, and I wanted to say that if you have a positive Q value, that's what I meant, that the reaction will be exothermic. And there's also a video that we went through. Basically, for this to happen, this must be positive, right? Let me see if I think in the next one, in beta decay 2, I have the explicit the assignment. In this one. So here we go. Okay, here we go. Decay. So also it's a positive Q value. For this to happen, Shoki, always you have a positive Q value, which implies that the reaction, the beta decay can happen, right? There's energy release for this to happen. A negative Q value will imply that it cannot beta decay. So when I asked you that question, I wanted you to investigate the possibility of positive versus negative, and remind yourself of something which is very common in nuclear, in chemistry reactions, where if you have a Q value which is positive, then it can happen spontaneously. If it's negative, you need to provide energy for that reaction to happen. That was the only point I wanted to make there. Okay, Shoki?
All right, thanks, Prof.
Is that did I answer your question?
Yes, Prof, you did.
Good. So it's about 12. I think Craig is right there waiting for you guys. Anything else? Any more questions? Guys, no more questions?
No, Prof, fine.
If no more questions, guys, it was a pleasure.